This is part 2 of section 9.2, the double angle formulas. Now, our main goal for today is to know the double and half angle formulas well enough so that we can actually verify trig identities. But first we're going to start with some basic applications of the double and half angle formulas so that we can work our way to the end to verifying trig identities. So as a little refresher, I've got our half angle formulas written out here at the top, and remember these are all derived from our double angle formulas, so as long as you know your double angle formulas really well, you can just manipulate those in order to get your half angle formulas. So in case you haven't watched it already, make sure you've already watched part 7 of your Prove It notes where you can see how we derive our half angle formulas. So let's begin now with problem number 1. We want to be able to express the cosine of theta to the 4th power in a form that doesn't involve a power of our trig function. Now, this is a really useful technique. So what we're trying to ultimately do here is reduce powers of, cosine. So this is a technique that you're going to use often in your trig identities. So you want to be really adept at being able to manipulate your double and half angle formulas. So the first thing I want to do here is try to rewrite cosine of 4 theta, or cosine to the 4th of theta, as cosine squared theta squared. Now what that's going to do is allow me to manipulate this a little bit, because I already know that the cosine squared theta, I know that identity. That's equal to 1 plus cosine 2 theta over 2. That's just a manipulation of your double angle formula. So now I can use substitution here and write that as 1 plus cosine 2 theta over 2 squared. So I've already reduced the power, because if you try to FOIL out the numerator here, you have 1 plus 2 cosine 2 theta plus cosine squared 2 theta all over 2. So again, I've already reduce that power here from the 4th to the 2nd power now. Alright, so I'm closer to where I want to be. I just need to get rid of this cosine squared 2 theta. Well, now I'm just going to reuse that same identity that we just worked on. Cosine squared theta is equal to 1 plus cosine 2 theta over 2, which means that cosine squared 2 theta, just again by substitution, would be 1 plus cosine of 4 theta over 2. So again, I come back over here and I rewrite this as 1 plus cosine 2 theta plus 1 plus cosine of 4 theta over 2 all over 2. So I've already been able to now manipulate this so that I no longer have a power of that trig function. So I've answered the question. I just want to clean this up a little bit and try to simplify it. Now the easiest thing to probably simplify this would be to just, oh, you know what? I think I messed that up because, yeah, I didn't square the denominator. Just realized that. So I didn't square the denominator here. Sorry about that. So that should be a 4 here and a 4 there. Now, when I multiply here, I'm still going to use that same idea. I'm going to multiply by 2 in the numerator and the denominator here so that I can get rid of that 2. So that I have 2 plus 4 cosine 2 theta plus 1 plus cosine 4 theta all over 8. And then simplifying here, the only terms that can simplify are the 2 and the 1 here to give me 3 plus 4 cosine 2 theta plus cosine 4 theta all over 8. So this is how I can reduce that power of that trig function by just using manipulations of my double angle formula. Okay, in problem 2, it asks me to express sine squared x times cosine squared x in terms of the 1st power of cosine. What that means is that eventually I want to whittle this down so that I only see cosine in my final answer and cosine to the 1st power. So let's start by just rewriting sine squared x and cosine squared x in terms of those double angle formulas that are slightly manipulations of that. So sine squared x is equal to 1 minus cosine 2 theta over 2. So I'm going to use substitution here and write that as 1 minus cosine 2 theta over 2. And then we already know that cosine squared x is 1 plus cosine 2 theta over 2. We just worked with that one extensively in the first question. All right, and then after this, let me erase here. I still have, so I'm good. I don't have sine anymore, so that's good. But if I were to multiply here, I do end up with 1 minus cosine squared 2 theta all over 4, right? If I were to manipulate this a little bit. So that's not quite what I want, because I want it in terms of the 1st power of cosine. So again, we're going to take that and rewrite that equivalently as 1 minus, since we know that cosine squared 2 theta is equal to 1 plus cosine of 4 theta over 2. Now I can get rid of that, that power here. And again, if I want to manipulate this and write this as a much easier expression, I can multiply by 2 in both the numerator and the denominator. So I clean that up a little bit, and I have 2 minus 1 plus cosine 4 theta all over 8, which gives me 1 plus cosine 4 theta over 8. So there I go. I've got it now in terms of just the first power of cosine. Okay, now in problem 3, this is going to be our first look at actually applying our half angle formulas. It wants us to evaluate the cosine of 105 degrees. Now this would be really tough for us to do because we don't have those values, those trig values memorized for a 105 degree angle. So this is why the half angle formula is really useful, because 105 is exactly half of 210 degrees, which is an angle measure that we do know the trig values for. So let's begin first, since it obviously gives us the hint of using a half angle formula. I'm going to write that out real quick. So I have the cosine of x over 2 is equal to positive or negative square root of 1 plus the cosine of x over 2. So I just want to point out to you that this value here, whatever's here, is exactly half of whatever's there. So we can just think of, one is double the other. So if I want to evaluate the cosine of 105 degrees, that's equal to positive or negative square root of 1 plus the cosine of 210 degrees. Exactly double, right? So again, it's just a manipulation of your double angle formulas. Okay, now there's some things we have to consider here. Obviously, we need to figure out what the cosine of 210 degrees is, but we also need to figure out about this positive or negative thing. Remember, it's not both, it's one or the other. So the cosine of 105, now that's that angle here, 105 degrees, is in the second quadrant. So that means that the cosine here should be negative overall. So I'm actually going to get rid of that positive. I know my answer here should just be negative square root of 1 plus whatever the cosine of 210 is divided by 2. So now we have to consider what is the cosine of 210. So if I were to draw, just to help me visualize where this is, 210 degrees is over here, and it's just below the x-axis here. So it's 30 degrees below the x-axis, which means that it has the longest x value here and the shortest y value. So our cosine here is going to be the largest value. So we have negative square root of 1 plus, and it's root 3 over 2, right? But it's also a negative since we're lying in the third quadrant here. So it's negative root 3 over 2 divided by 2. So now to simplify this a little bit, I'm just going to multiply like we did in the problem above. I'm going to multiply by 2 in the numerator and in the denominator to just simplify this a little bit more. So now I have negative square root of 2 plus negative root 3 all over 4. Okay, so again, I want to clean this up slightly, and I can because I know what the square root of 4 is, so that's pretty nice in the denominator here. But I'll end up with negative square root of 2 minus root 3 all over 2. So that's as far as we want you to simplify that, because otherwise it gets a lot uglier. This is as good as it gets, all right? All right, in our last problem before we get to trig identities, it asks us to express the sine of 2 theta and the cosine of 2 theta in terms of just x. It gives us the fact that x plus 1 is equal to 3 times the sine of theta, and theta lies in the second quadrant. So let's begin here by writing sine of 2 theta. All right, now I want to express this in terms of just x. If I go back to my given here, it says that x plus 1 is equal to 3 times the sine of theta, which means that the sine of theta is equal to x plus 1 over 3. So I want to rewrite sine of 2 theta so that I can write it in terms of sine theta. And I know that from my double angle formula, the sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. So now by substitution, I know that that's equivalent to 2 times x plus 1 over 3 times the cosine of theta. So I'm one step closer now. I need to be able to express the cosine of theta, though, in terms of just x. So what I'm going to do is use a manipulation of my identity cosine squared theta plus sine squared theta equals 1. I know that if I want to solve for cosine of theta, that's equal to positive or negative square root of 1 minus sine squared theta. Now in this case, because my cosine, because my angle is in the second quadrant, the cosine of theta here has to be negative. So this is a negative value. Okay, which is going to change just slightly. Obviously I get rid of the positive, it's just going to be negative square root of 1 minus sine squared theta. So if I use substitution, so I have x plus 1 over 3 times negative square root of 1 minus, and instead of writing sine squared theta here, I'll substitute in sine of theta. So that's x plus 1 over 3 squared. Okay, and I'm just going to I'm not going to clean much of this up. I'll just put that negative out in front. So I have negative 2 times x plus 1 over 3 times the square root of 1 minus x plus 1 over 3 squared. And that is how I would express the sine of 2 theta in terms of just x. All right, let's answer the second part of this question, which says to express the cosine of 2 theta in terms of x. So if I want to rewrite the cosine of 2 theta, I've got lots of different manipulations of that double angle formula that I can use. The one, though, that suits me the best here is actually 1 minus 2 sine squared theta, because I already know what sine of theta is in terms of x. So if I just use substitution here, I have x plus 1 over 3 squared to substitute in for sine of theta. So that's pretty easy, and that's my answer actually for cosine of 2 theta in terms of just x. All right, now for the fun stuff. Let's verify some trig identities. In problem 5, I see that on the right-hand side here of this expression, I have 1 over the cosine of theta. So that tells me something. That tells me I want to get rid of anything that isn't a cosine in the left-hand side. So I definitely want to try to get rid of the sine of 2 theta over sine of theta and rewrite that in terms of just cosine. So I'm going to begin first working with the left-hand side, because clearly that is the more complicated side here. And I'll write that as 2 times the sine of theta times the cosine of theta. So I'm just applying a double angle formula there over sine theta. So let's just rewrite this part too. Okay, now that was helpful because those cancel, and it leaves me with just 2 cosine theta. So I've already gotten rid of the sine of theta, which is great. But now I see that I have a cosine of 2 theta, and in the right-hand expression here, it's just 1 over cosine of theta, so it's not in terms of 2 theta. So again, I want to apply a double angle formula here. Now, there's a few that I can choose from, especially when dealing with the cosine of 2 theta. So let's start with some of them. If I try cosine squared theta minus sine squared theta, that's not really a good one to pick for the fact that I'm introducing, again, a sine squared theta, right? I don't want to do that again. I want to get rid of the sine of anything else. So let's try a different one. What if we did 1 minus 2 sine squared theta? Well, that would be dumb too, because I'm again introducing a sine theta in there. The other one that I'm thinking about using would be 2 cosine squared theta minus 1. Now that one's going to be really helpful here, because if I rewrite this, so I have 2 cosine theta minus, let's put that in parentheses, 2 cosine squared theta minus 1 all over cosine theta. Alright, now I don't see anything in terms of a sine, so that's really nice. And let's see, this would distribute here and here, right? So I have, let's write this, kind of running out of room here, let's write it up here. So I have 2 cosine theta minus 2 cosine squared theta plus 1 over cosine theta. So it should be plus a negative 2 cosine squared theta. So I just distributed that negative, in case you're wondering what happened and why that changed to a plus 1. Alright, and then if I actually split up this fraction, you're going to see that that would be very helpful here, because I have negative 2 cosine squared theta over cosine theta, and then plus 1 over cosine theta, which is right here, secant theta, right? Well, this here, let's do this in red, highlight this. That's going to be 2 cosine theta minus 2 cosine theta, since I cancel out one of the powers of cosine there. So this is very helpful for me, because this cancels and leaves me with 1 over cosine theta, which is secant theta, and I'm done with my identity. Okay, the next problem here, number 6, I think is a little bit misleading, because if you go based off of one of our strategies of trying to attack the more complicated side, you would probably want to start with the right-hand side here. In this case, what happened when I tried the right-hand side, I ended up not being able to, I was going in circles, and I really couldn't rewrite it in terms of the 3 theta here, so instead, I started on the left-hand side, and I found that that was a little bit easier. So if we start on the left-hand side, I can rewrite the sine of 3 theta as the sine of 2 theta plus theta. Okay, and by doing that, I end up being able to write that with a double angle formula in there as well, but I'm going to use my addition formula, sine, cosine, cosine, sine. So I have the sine of 2 theta times the cosine of theta plus the cosine of 2 theta times the sine of theta. Alright, now, so that's again the left-hand side here. Now I see this sine of 2 theta here, and this cosine of 2 theta. So I want to try to rewrite those. Now, the sine of 2 theta, the one that pops out at me, is the 2 sine theta cosine theta, right? That's really the one identity, double angle formula that we use a lot. And this ends up being really helpful because if you look at this, you have cosine squared theta, which is right here. You have 2 sine theta cosine squared theta. So we're really close now. We just are off by a factor of, an additional sine theta cosine squared theta. Now, out of this second portion here, cosine 2 theta times sine theta, we need to get the remaining sine theta cosine squared theta and the negative sine cubed theta. Okay? So let's change that up by manipulating the cosine of 2 theta here. We've got a few different identities. Now, if I tried, let's start with 1 minus 2 sine squared theta. So if we tried that one, that's not going to be very helpful. Even though it does give me a sine cubed, it doesn't give me just 1 sine cubed theta. It gives me 2. And it also doesn't give me a cosine theta at all. So I wouldn't want to use that one. Okay? So let's try a different one. If we, let's say, tried 2 cosine squared theta minus 1 times sine theta. Now at least I have the cosine squared theta that I'm looking for times sine theta, but it's too much, right? It's 2, and I don't want to have 2. I just want 3. I need the 2 plus 1 additional sine theta cosine squared theta. So that doesn't help me either, plus I don't get a sine cubed here. So I don't want to try that one either. In this case, I want to try the cosine squared theta minus sine squared, oops, forgot the minus sign. So minus sine squared theta, identity here. So I times sine theta. And now if I multiply that out, I have cosine squared theta times sine theta minus sine squared theta times sine theta gives me sine cubed theta. Okay, and if I just add these like terms here, I have 3 sine theta cosine squared theta minus sine cubed theta. Alright, and that is exactly what I tried to show. Alright, I'll let you guys try problem 7 here on your own. This is a really good one for you. It's even trickier than number 6, but it follows the same idea. So start with the left-hand side here and try to arrive at the right-hand side. Notice that you do not want any sines here at all. You want to just have everything in terms of cosine. So please go ahead and try problem 7 on your own. Okay, in our last identity here, I see that I have all cosines on the left-hand side and only sines on the right-hand side. And in this case, starting on the right-hand side, this is actually the more complicated side here because you have the sine of 8 theta here, which you can continue to try to reduce using your double angle formulas. So that's what I'm going to focus on, is the right-hand side here. So I would begin here by applying a double angle formula and writing that as 2 times the sine of 4 theta times the cosine of 4 theta. And so already right away I've introduced the cosine of 4 theta, which is good since I want it in terms of a cosine of 4 theta. So I have that over 8 sine of theta. Now in this case clearly that 2 over 8 will reduce, so I'm going to rewrite that as just over 4 sine theta. Okay, and then I'm going to continue to try to reduce. I'm going to leave that cosine 4 theta alone because I want to have a cosine 4 theta. So let's just focus on the sine of 4 theta here. We'll apply another double angle formula, identity, and write that as 2 sine of 2 theta cosine of 2 theta times the cosine of 4 theta all over 4 sine of theta. Now again, I see that I have that 2 over 4 here, so I'm going to simplify that and write that as 2. Oops. So 2 sine theta. And then I'm also going to leave this cosine 2 theta alone again because I see that I want to have a cosine 2 theta. And then finally, I'm going to take that sine of 2 theta. I don't want to see a sine 2 theta anymore, so I'll use a double angle formula here and write that as 2 sine theta cosine theta times cosine 2 theta times cosine 4 theta all over 2 sine theta. And what's nice about that is that the 2's will cancel, the sines will cancel, and it'll leave me with cosine theta times the cosine of 2 theta times the cosine of 4 theta, which is exactly what I was trying to show. All right, that is the end of your lesson for today. You will get a lot of practice with these proofs. Obviously, no two proofs are the exact same, and you could have done this exact same proof a lot of different ways than I did. Hopefully, I chose one that makes sense to you. If you find that you used a different step or a faster, more efficient way of doing the same problem, please make sure you show me because I would like to see it too. So good job. I'll see you guys tomorrow in class.